This is the second lecture of the third week, and it's going to cover the binary regressor. So far, we've only discussed cases where independent variable and dependent variables are continuous. So in our policy question, we had a test score and student-teacher ratio, which are both continuous variables. Sometimes you may have a binary independent variable. We call this dummy variable sometimes. So there are cases when we're interested in the difference between female versus male, or whether a district is small versus large, or in case of randomized control trial, whether a group was treated or not. So far, we've interpreted beta 1 as a slope, but when you have a binary variable, what would the beta 1 mean? Let's go back to the policy question, where the student-teacher ratio and test scores were both continuous variables. Let's say that now we're only interested in if the small class or large class size affects test scores. So we're going to define small class as the student-teacher ratio being less than or equal to 20, whereas a large class as student-teacher ratio being greater than 20. We're going to call this dummy variable small underscore CLS. So now your new regression model looks like this. The test score is equal to beta 0 plus beta 1 times this small class dummy variable. If you want to know the average test score of a large class, then your small class dummy would actually equal to 0. So you plug the 0 into the model, and you'll have beta 0 as your average test score for the large class. If you want to know the average test score for small class, in this case, your dummy small class would equal to 1. So you plug 1 into this regression model, and you'll have beta 0 plus beta 1. So if you want to know the difference between the test score of the large and small class, basically you'll have beta 0 minus beta 0 plus beta 0, 1. And all you have left, I guess it should be the other way around, beta 0 minus beta 0. So beta 0 will cancel out, and all you have left is beta 1. So in other words, beta 1 is the difference in test scores between the two groups. Here's an example of dummy variables using actual numbers. So previously, we said that the average test score of large class is when the dummy variable is what we call small class previously is equal to 0. And when this dummy variable is equal to 0, the average test score becomes beta 0. So that's how we get beta 0. We also said that the difference between the average test score is equal to beta 1. So we subtract the average test score of large class from small class, and that's how we get 7.4 as beta 1. The standard error of beta 1 can be calculated using this formula. And you can plug in the standard deviation and the sample size into the formula to calculate the standard error of beta 1. But you never have to calculate this by hand, so you don't have to worry about memorizing. So just to summarize what we have learned in this lecture, beta 0 is a mean of y when x is equal to 0. So when you plug x equal to 0, you only have beta 0 left. Beta 0 plus beta 1 is the mean of y when x is equal to 1. So this makes beta 1 as a difference between two groups. The t-statistics and confidence intervals are constructed as usual, and this is using a dummy variable is an easy way to do differences in means analysis. This dummy variable regression model becomes especially useful when you have other additional regressors.